All right, we're back to finish up section 2.5. We'll start with number 5, find dy dx. And so you can see that they're multiplied together, so we're going to be needing a product rule. U prime v plus uv prime. The u will be the x squared, of course, so u prime will be 2x. So we have 2x, u prime v, which is just y to the fifth, and no parentheses necessary here because it's just v, not v prime. Okay, so u prime v plus u, which is x squared, times v prime, which is 5y to the fourth. Now that is the wrong letter, dy dx. All right. Equals 18. Nope, just kidding, 0. Remember, you have to take the derivative. Don't leave the 18 there. People do that. All right. Let's get the dy dx by itself. I will subtract and then divide. Okay, there's the subtraction. The 2x y to the fifth is gone from the left-hand side. And I kind of tidied up the left-hand side. It's 5x squared y to the fourth. I like to put the coefficient first, put the variables in alphabetical order, just a little smoother sounding. And now I'm going to divide by that very thing, the 5x squared y to the fourth on both sides. All right, so dy dx is that, but that's not simplified. Since there are no addition or subtraction signs, I'm free to cancel, and I should cancel. That's my expectation of you guys. Simplify it down for me. Your poor teacher who's got to grade all this stuff. The -2 and the 5 hold their spots. The x's, there's going to be one x in the denominator, and 5 minus 4 for the y's. There's going to be a y in the numerator, and man, that looks a lot nicer than what I just had. That is the derivative dy dx. Number 6. Ooh, we want a second derivative. Remember, that's the notation for the second derivative. Nothing's getting squared. It's just a weird way to write it. But again, it's not anything I invented. I'm just the messenger here. So, all right, let's take two derivatives. First derivative will be, well, it's going to be implicit. So it's 3y squared. But that's the wrong letter, dy dx. Equals 4x. All right, I'm going to divide both sides by 3y squared. The 3y squareds are gone. And there's your first derivative. Dy dx is 4x over 3y squared. The second derivative, which I'm going to do in blue, is the first derivative's derivative. But since the first derivative is a fraction with variables in both the numerator and denominator, I need to use the quotient rule. So again, the numerator always is the u. The denominator has to be the v. And it's going to be u prime v minus uv prime over v squared. All right, so here's the second derivative. Let me make a very large fraction bar. V squared, I'll do that first because that's easier. 3y squared times 3y squared, that's going to be 9y to the fourth. And again, no parentheses, no chain rule needed because it's not a derivative. I'm just squaring it. Okay, up in the numerator, we have u prime v. Well, u prime is just 4. And v is just what it is, which is 3y squared. U prime v minus u. Copy that down. V prime. V prime is going to be 6y. Oh, but that's the wrong letter. Dy dx. But instead of writing a dy dx, I already know what dy dx is. It's that green fraction. And the expectation is to put the fraction back in. College Board, a lot of times on the FRQs, on the free response questions, will say, find the second derivative in terms of x and y. And they come right out and say in terms of x and y. That's their polite way of saying, get the stupid dy dx out of there. We only want x's and y's in the answer, not dy dx's. So they expect you to do what I'm about to show you. All right, so we put the first derivative in where the dy dx was. Unfortunately, we have now created a fraction within a fraction, which is never okay. And so I have to deal with it. Let's see what this all becomes. I am going to simplify this a little bit. I'm going to bring it up top. That's 12y squared minus. Now this y does cancel with the squared at least, but I've got a mess. The 6 and the 3 are also going to cancel. That'll become a 2, the 3 becomes a 1. But still, man, we got 4 times 2, that's 8, times under 4, that's 32. So minus 32x squared over y. And that whole thing is over 9y to the 4th. All right, so that's the answer. But you're never going to leave an answer like that. That's just awful. So instead, what you want to do is get rid of the fraction within the fraction thing by multiplying by a giant 1 in the form of a y over y. In the numerator, which I'm going to put some parentheses around, what will happen is you're going to get 12y to the 3rd, but then this is going to be nice. The y's will cancel, which is why we're doing this. Okay, those will cancel out. So let me come down here in red, and I'm going to write what I have now. So we have 12y to the 3rd. This is an improved answer. Minus 32x squared over 9y to the 5th. Remember, there's a 1 on that. There we go. And that's the answer I fully expect to see. Not that other unsimplified stuff. All right. Let's take a look. Wait, what? No. The teacher's worst nightmare. This is the right problem, right? Number 6. That answer looks nothing like my answer. What the heck? What's this little thing? So cute. What are you? Ah, hey! It's my answer. Guess didn't really think I was lost, did you? Oh, man. So those answers are the same. But who knew? It's really hard to tell. This is so deflating, though, for students who maybe don't realize that those are the same answer. And worse yet, you get onto a standardized multiple choice question, and the choice is what you see in the box, and your answer is what's in the oval, and you don't realize they're the same thing. And here you did everything perfectly right, and you get 0 credit for your work. And that is just disturbing as all can be. So I've got to convince you that they're the same, and I have to also equip you with a way that you can realize that they're the same. So whenever this happens, and you're sure that you're right, but the answer looks completely obnoxious or different, what you want to do is look back at your original problem. Back in black, as AC/DC says. Y cubed equals 2x squared. Let me get rid of all my blue and green stuff. And we'll work a little algebra to prove to you that the answers are the same. I noticed that in their answer, well, that's actually my answer, there are no x's. And so I need to get rid of this 32x squared. Obviously, it's not welcome. So I come back over to here and I'm thinking, what if I multiply these both by 16? And you're thinking, Mr. Lewis, why 16? I'm like, well, if you multiplied it by 16, you'd have a 32x squared, which matches what I have over there. Over here, it'd be 16y cubed. So if those two are in fact the same thing, why don't I just come over and replace the 32x squared with a 16y to the 3rd. And I'm just messing around here. So 12y to the 3rd minus 16y to the 3rd is negative 4y to the 3rd over denominator. And now I think you can see what's happening. Now you are allowed to cancel 3 y's. And you do get a more simplified answer. It only has one variable in it instead of 2, so that's an improvement. And that is negative 4 over 9y squared. So there are problems in the textbook like this where, you think you're good, you look at your answer, you're not matching the back of the book, you're like, go back to the original problem and see if there's some token substitution you can do to make it match. Because the expectation is that you are all the way simplified. And that way you're safe on anything multiple choice wise. You're not picking none of the above, choice D. That'd be so unfortunate. All right, halfway done with day 2. 2 more to go. Here's number 7. Okay, for these last 2 problems, the directions are slightly changed. It says find dy dx and the equations of the tangent and normal lines, which is what we were doing earlier in the chapter. The problem is we couldn't have solved this earlier in the chapter because we didn't know about implicit differentiation. This is also a sideways parabola, which means it's not a function, and therefore most graphing calculators won't graph it. So, All right, let's try it out. Let's plow through straight from left to right, taking the derivatives as we go. I've got a 2 times stuff to the first. Oh, but that's the wrong letter. dy dx. You're good. You're forgiven. Why, thanks. Equals. Now keep in mind the right side is just 8x plus 48. The derivative of that would just be 8. Okay, so far so easy. Let's divide both sides by the 2 and y minus 3. Of course, you can cancel the 8 and the 2, so I will. And dy dx, now that this is also canceled, is equal to 4 over y minus 3. Okay, so that's the first thing that I wanted you to do. Now the next would be to find the equations of the tangent and normal lines. And if you're using point slope form, this is really a 2-for-1. In both cases, we know that you're going to go through the point -4, -1. So that was easy. Now we just have to use the slope. And this is the first time where the derivative has actually just had y's and no x's at all, which is kind of cool. All right, so the y gets plugged in, and the y is the -1. So in it goes, -1 minus 3. That's going to be 4 over -4, which is -1. So the slope is -1. And then the normal line, the reciprocal of -1, is just +1. And that's it. Now, obviously, you don't have to write the 1s. You do need the negative sign on the tangent line. To check this, because my graphing calculator will not graph it, I went to Green Globs, which will, and Desmos will as well. So I typed in the original parabola, the sideways or sleeping parabola, the y minus 3 squared equals 8 quantity x plus 6. Here's what it looks like. All right, you can see that it does go through the point -4, -1. All right, let's watch what our tangent line is going to do. Hopefully it will skim right past the point -4, -1. And there it is. And obviously the normal line will go through the same point because I'm not changing the parentheses. It'll just have a slope that makes it perpendicular. All right, our answers have been verified. There it is. And again, because that's not a function and it's opening sideways, we needed implicit differentiation. That's why we wouldn't have been able to do that problem a couple sections back, but now we can. All right, this last equation is a circle. You can tell because x and y are both squared. They're both positive. They both have leading coefficients that are equal to each other, in this case, both 1s. Even if you didn't realize it was a circle, you could figure out that it's a circle and get it in graphable form by completing the square twice. I don't really have an interest in that. I'd rather use calculus. It's easier and quicker. So let's find dy dx. Okay, from left to right, it looks like this. 2x plus 2y. Whoop, wrong letter, dy dx. minus 2 equals 3 dy dx. And again, the derivative of positive 13 is 0, like every constant. Let's go ahead and subtract 2y dy dx from both sides. All right, that drops out. So that's just a 2x minus 2. The right-hand side, they both have dy dx, so I'll factor it. Divide both sides by the 3 minus 2y. That will reduce out, cancel out. All right, so we've got our derivative, 2x minus 2 over 3 minus 2y. Let's get the 0.35 plugged into it. Keep in mind that x's are 3's, the y's would be 5's. That's going to make 6 minus 2, that's 4. And 3 minus 10 is negative 7. So the slope of the tan line will be negative 4/7. The slope of the normal line will be positive 7/4. We're at the 0.35, so our equations are ready. All right, as I just mentioned, the slope of the tan line is negative 4/7. And the normal line being perpendicular is positive 7/4. And there they are. All right, and of course, last but not least, I want to go back and check my answer on green globs. I just want to feel the glory of being right, to be honest. But it's always good to check. And again, you can check it on Desmos if you want. That's a great program as well. All right, well, it turns out that green globs will not allow me to type in the equation until I complete the square twice. I'm not willing to do that, so I'm going to go ahead and go to Desmos, where it will allow me to type in basically anything I want. And I'll go ahead and put the equation of the circle in there. And as you can see, my mouse is right at the 0.35, as we should be. So I want the tan line to go right past there. And you can see my answer for the tan line is a perfect hit, as is the green normal line, not too surprisingly. So that's it. So now we can actually use circles and other things that aren't functions and still find tan lines to them, which is really useful. Brings me back to my younger years in science class when we were learning about centripetal force and all that good stuff. We only have one more section left in the chapter. It's a big one, related rates. Come with your A game for that, but that'll be 3 days, and then we'll be done with chapter 2. So until then, take care of yourselves. Catch you later.